Welcome to all on Sethi system. In today's session, I am going to discuss electric charge and field part 2 for CBSE purpose. In the part 1, I have already discussed Coulomb's law and properties of charges. That session will also attach with this one, right? Now, in this chapter, I am going to discuss electric field due to dipole on an axial line, equatorial line, and any point. Dipole and uniform electric experience torque and have potential energy rotation. Gauss Theorem and its application. 5 numbers application. In this case, I am going to discuss 5 numericals. 5 numerical question. One on force due to electric field and weight balancing. Second, torque. Third, potential energy. Fourth and fifth, Gauss Theorem. One by one. All these points are very important for the purpose of CBSE board, state boards, as well as for the entrance purposes for all these. Therefore, it is requested, please go through the complete session. Right, now let's start the question. Concept applicable in the solution. Electric field intensity at any point due to source charge is defined as the force experienced by unit positive charge or negative charge. That is the positive charge. What is the essential condition? Charge placed at that point without disturbing. No disturbance should be there of the source charge. Mathematically, E equal to F by Q. It is a scalar quantity or vector quantity? It is a vector quantity. This dimension, you know E equal to F by 2. MLT minus 2 divided by AT. Charge की dimension AT. So MLT minus 3, A minus 1. Direction is positive to negative, or you can say away from positive charge towards negative charge. Right? Next, electric field due to point charge is given by E equal to 1 over 4 pi epsilon naught Q upon R square. Electric field due to point charge. Electric field at any point in space due to charge depends only on the distance. That means the magnitude activity due to point charge is same at all points of a sphere. Therefore, it has a spherical symmetry. Electric field due to point charge have a spherical symmetry, right? Let's start the question. Question is 6 microcoulomb. One string is there, one is there, 6 microcoulomb. This is weight mg plus 6 microcoulomb and electric field is acting downward. Then, what will be the tension in the string? Tension, you know, this is the string tension, it is the weight, and force due to electric field will be Q into E. According to free body diagram, the resisting tension will be net downward force will be equal to the upward force. Downward force equal to upward force. No. Downward force means weight is acting plus electric force due to electric field. QE equal to tension. In this case, mass is given, acceleration due to gravity is known, charge is known, electric field is known. Electric field is given in this case is 400 Newton, electric field 400 Newton per coulomb. So, substituting all the values, we will get the answer. Tension will be equal to 1.22 into 10 to the power minus 2 Newton. Right? This was the case 1. Case 2. Case 2 will be when charge is replaced by -6 microcoulomb. Then the electric force due to this will be like this. In that case, mg equal to T plus QE. T will be equal to mg minus QE. Substituting the values. On substituting the values, we will get the answer 74 into 10 to the minus 4 Newton. I think this is clear. Now, next, what are electric field lines? Electric field line is a curve in such a way that tangent to it, at any point in each is in the direction of electric field at that point. Electric field line in space, it is a curve in 3 dimensions, right? Electric field density is of lines is more near the charge, and away from the charge the field is weak, so density of field lines is less, right? Now, property of electric field lines. Direction of electric field lines is away from positive, radially outward. Like next, property of electric lines. Electric field lines start from positive charge, and terminate at negative charge. That's terminal. In case of single charge, this may start or end at infinity. Third, tangent at any point on electric field line shows the direction of electric field at that point, right? Next, two electric field lines never intersect each other, because if they intersect, the two tangents drawn at that point will represent two directions at that point, which is not possible. Next, in a charge-free region, electric field lines can be taken to be continuous with curve without any breaks. Electric field lines are perpendicular to surface of charged conductor. Electric field lines contract lengthwise to represent attraction between the two unlike charges. Electric field exert pressure sideways pressure to represent. These are the 7 properties I have discussed. Again repeating, electric field lines start from positive and terminate at negative. Direction of tangent and would give the direction of electric field. Two electric fields never intersect. If it intersects, two directions will, which is not possible. Electric field lines can be taken to continuous curve without any breaks. Electric field lines are perpendicular to the surface of the charged conductor. Electric field lines contact lengthwise to represent attraction between the two unlike charges. Electric field lines exert sidewise pressure to represent repulsion between the two like charges. Now, representation of electric line fields. Electric field lines always point away from the positive charge and towards the negative, as already discussed. In fact, electric originate at a positive charge and terminate at a negative charge. This is for uniform field, this is for non-uniform magnetic electric field, right? Now, this is direction in from positive charge, radially outward. This is radially inward. The electric field lines start from positive charge and end at the negative charge. In this case, you say, in this case, Q1 charges are same. Q1 equal to Q2 positive charge. In this case, Q2 is greater than Q1. So, in this case, it is denser. In this case, equal density is there. In this case, you can observe the difference of densities, right? Next, Conductors in electrostatic field. Electric field, electric field light do not pass through the conductor, hence the interior of the conductor is free from the influence, free from the influence of electric field. In this, electric field is equal to 0. Total charge of charge conductor lies at its outer surface of the conductor. The magnitude of the field strength at any point on the surface of the conductor is proportional to the surface charge density. Surface charge density at that point. This is all about this thing. Now, next chapter, I will discuss the dipole, regarding the dipole. Let's start the dipole. Now, the topic is electric dipole. Question is, what is the magnitude of electric field intensity due to dipole of moment 2 into 10 to the minus 8 coulomb meter at a point, distance 1 meter from the center of dipole, when the line joining the point of the center of dipole makes angle 60 degree with the dipole axis. This question is applicable for 12th standard, JEE main, NEET, CUET and other entrance examinations. Before the solution of this question, I will discuss a certain concept applicable. First of all, electric field intensity to dipole at any point. I am going to discuss, suppose this point is A, this point is B, minus Q plus Q. What is the axle line? Axle line joining these two. Suppose we find the electric field intensity at this point. E axle will be 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, 2 PR upon R square minus A square to the power 4 square. Right? Now, and in the case of approximation, 1 over 4 pi epsilon naught, 2 P upon R cube along, in this case, this is the point BP produced. That is same in the direction of dipole. What is the dipole? Dipole is P equal to any charge into separation, and direction is from negative to positive, right? Direction is negative to, it is same in the direction of dipole. Electric field due to dipole at equatorial point. Equatorial point is, suppose the center of this, we take this perpendicular bisector and this point would be, this is the point P. In that case, electric field intensity due to this, away from positive charge towards negative charge. On resolution, we will get along this direction. In the equatorial is 1 over 4 pi epsilon naught P upon R square plus A square to the power 3 by P along, this is anti-parallel to this, along BA, parallel to BA. This is in anti-parallel to dipole moment direction. What is the relation? E axial is equal to magnitude wise to equatorial, right? E axial equal to twice equatorial. Now, at any point it is given by E equal to 1 over 4 pi epsilon naught P under root 3 cos square theta plus 1 divided by R cube, right? Next, now in this question, and direction of theta, tan of alpha is equal to 1 by 2 tan of theta. These are the two at any point. Now let's start the question. What is the question? Question is, what is the magnitude electric field intended dipole? Dipole moment P is given, 2 into 10 to the minus 8 coulomb, distance given, angle given. Means theta is given 60 degree. P is given 2 into 10 to the minus 8 coulomb meter. And R is given to you, distance 1 meter. Right? Just substitute the values. On substituting, we get electric field density on simplification 238.1 Newton per coulomb. Electric field density 238.1 meter per coulomb. Now I think EXL is this one, E equator is this one, relation is this one, and at any point is this one, right? I think all directions I have discussed very well. In case of equatorial, anti-parallel to dipole moment. In case of XLN, parallel to dipole direction. And in case angle, tan alpha equal to half of angle tan of theta. Next, I will going to discuss Gauss's theorem. Gauss's theorem. Electric field, dipole in a electric field. An electric dipole of the moment, this is aligned to uniform electric field. This, yani, P is given to you. This is P, this is E. Calculate the potential to hold the dipole at 60 degree with the direction of electric field. Let's start. We know dipole and electric. One is torque. Torque is P cross E. Cross product of this. That is PE sin theta into unit vector in the direction of this. So direction of torque will be, suppose one is P, one is E. PE, this is theta, this will be 90 degree, this will be 90 degree. Perpendicular to both the directions because cross product. Answer is AB sin theta into unit vector perpendicular to both the vectors. So this is P cross E, right? And next, work done in dipole. Work done PE potential energy equal to minus PE cos theta 2 minus cos theta 1. Cos theta 2. In this case, theta 2 is given to you 60 degree, theta 1 is given to you 0 degree. Moment is given to you, that is 5 into 10 to the minus 8, and electric field is given to coulomb meter, and that is given to 1.44 into 10 to the power 4 Newton per coulomb. In that case, now formula is available with us. P is known, E is known, cos theta cos 60 minus cos 0, that is PE. P की value put को, E की value put को, that is electric field. That comes out to potential energy or work done. That comes out to be simplification 3.6. You can solve it into 10 to the power minus 4 joule. In this case, most important thing is to how to identify theta 1 and theta 2. That is the only basic in this case. Initially, angle is theta 1. Hold dipole to hold at 60 degree with the direction of electric field. In initial theta 1, 0 degree, theta 2, 60 degree. Solve it. Next, Gauss's theorem. Question is 5 charges plus Q, 5Q, plus 3Q, minus Q, minus Q are situated as shown in the figure. The electric flux due to this configuration through S is. Question is taken from JEE Mains 2024 and applicable for all these. Before we start with the question, let's discuss certain concept applicable. Gauss's theorem. The surface integral of electric field intensity over any closed surface, that is known as Gauss theorem, in free space is equal to 1 over epsilon naught times the net charge enclosed within the surface. Net charge. This is the Q is net charge inside the surface. The net charge inside the surface. Let's see. Let's start the question. In this case, we have to find the electric flux. Electric flux phi E equal to one is E dot ds or 1 over epsilon naught Q net inside the surface. Q net will be equal to Q net is inside 5 plus 6 minus 4. 5Q 1 over epsilon naught 5Q plus Q minus 2Q. That is 4Q upon epsilon naught. This is the answer. This was the application of Gauss theorem. How to consider the charge. D is the correct option. D is correct option. D is correct option. Next question is, an electric flux is given by 6I plus 5J plus 3K unit. The electric flux through a surface area is 39 meter per second lying in YZ plane. We know electric flux is dot product of also E dot ds. E dot ds, right? Now, it is given to you E 6I plus 5J plus 3K dot 30I. You know, area vector is always perpendicular to the surface. In this case, lying in the YZ plane. YZ plane is that is in the along axis, that is perpendicular to that, right? On we know I dot I equal to 1, I dot j 0, I dot k 0. Simple property. On simplification, we get 360 plus 0 plus 0. That comes out to be 360. What will be the unit? What will be the unit? Electric field unit and that unit. That is C option is the correct. Electric field unit Newton per coulomb into meter square. 360. Option C is correct. Now, I am going to discuss the application of Gauss's theorem. Application of Gauss's. Now, application of Gauss's theorem, and before discussing this, electrostatic force due to continuous charge distribution. What is continuous distribution of charge? The region in which charges are closely spaced is said to be continuous distribution of charge. It is of the following type. Linear charge, it is represented by lambda. Linear charge density is defined as the charge per length of linear charge distribution. In this case, force is given by 1 over 4 pi epsilon naught, that is lambda dl upon r naught square r naught cap. Right? Lambda is the linear. Surface charge density. Surface charge density in this will be surface area. It is two-dimensional. It is denoted by sigma. It is denoted by sigma. In this case, force will be equal to 1 over 4 pi epsilon naught s sigma ds upon r naught square r naught cap. Volume distribution charge, it is denoted by rho. Volume charge density is defined as the charge per unit volume charge distribution. In this case, force is given by 1 over 4 pi epsilon naught volume rho dV upon r naught square r naught cap. This is all about the continuous distribution of charge. That is the linear one, surface one, volume one. Linear, lambda, surface, sigma, volume, rho. Right? Now, application of Gauss's theorem. Application of Gauss's theorem. Electric field due to some metric charges configuration using Gauss's law. Electric field due to infinitely long thin straight charge wire is given by electric field is given by 1 over 4 pi epsilon naught twice lambda by r. Twice lambda by r. All derivations are important. You can go through it. Right? Now, this is the end result. In this case, this is the Gaussian surface. Electric field is on account of this, on account of this, on account of this electric field is 0, on account of this for curved surface electric field is considered, that is 2 pi r. From this you have considered the electric field, right? Next, variation of electric field. Variation of electric field is as it is inversely as E inversely proportional to R. It is known as rectangular hyperbola. Rectangular hyperbola. This is rectangular hyperbola. It decreases like this. If lambda is greater than 0, the direction of electric field at every point is radially outward. If it is less than, that is inward. Right? Next, field due to thin, infinite plane sheet of charge. In this case, E comes out to be sigma over epsilon naught. E comes out to be sigma over epsilon naught. And if the infinite plane sheet of charge has a uniform thickness, E upon 2 epsilon naught. In this case, E comes out to sigma over epsilon naught. E is independent of R, the distance of point from plane charge sheet, right? Now, simple formula in this to derive it, take the left hand side of the Gauss's theorem E dot ds and equal to 1 over epsilon to goes. Electric fluid to infinite. There are 3 regions. Region 3, that will be equal to 1 over 2 epsilon naught sigma 1 over sigma 2. In this case, minus 1 over 2 epsilon naught sigma 1 plus sigma 2. In this case, 1 over 2 epsilon naught sigma 1 minus sigma 2, considering this is greater than this. Next, electric field due to non-conducting charge solid sphere. In this case, these are the formulas applicable in this case. E inside is rho r upon 3 epsilon. E on the surface, put r equal to radius of that is rho r upon 3 epsilon. And outside, जो actual formula होता है उसको लगा दीजिए upon r, जो formula लगेगा that. Right? What is the graph? As we say, inside E is directly proportional to R. So this is a straight line. This is the straight line. Maximum is at the surface and then decreases like this. Right? This is all about the field. I have just only discussing the formulas which are applicable for this. Derivation may be carried out or will be discussed in another session. Right? Field due to uniformly charged thin spherical cell. Thin spherical, that's sigma. This is the uniform surface charge that is thin spherical cell radius r. The Gaussian theorem is spherical. Then outside will be E equal to 1 over 4 pi epsilon naught Q upon r square. And so on the surface E equal to sigma over epsilon naught. And at a point inside the 0, that will be equal to 0. Right? This is all about this thing. A variation is given to inside it is 0, maximum surface, then it starts increasing. I have discussed the 5 cases. I will discuss the 5 cases here, right? Now, I would like to request, if you are new to my YouTube channel, Sethi Learn, and like this video, please subscribe and share the channel and press bell icon to receive updates on concept killing videos as well as on quick revision formula sheets. Quick revision formula sheets on 11-12 standard. थैंक यू, धन्यवाद, बहुत बहुत धन्यवाद, बहुत बहुत धन्यवाद।